Methaforming is a catalyst and process that converts naphtha and ethanol or other alcohols into gasoline at 1/3 the current cost at comparable yields. And I'll be focusing in this presentation on the additive benefit that if the alcohol is ethanol, then methaforming reduces CO2 emissions by 1/2 ton per ton of naphtha. This is of growing value around the world. I've presented methaforming many times, and many of you've probably heard, so I'll briefly review the process, and it explains why the cost is 1/3 of the competitive alternative. To best understand this, I'll give you a brief review of the process. Methaforming is a one-step conversion of naphtha with ethanol into gasoline. It operates at modest pressure of 5 to 10 atmospheres and modest temperature, 370 centigrade, in a process much like a hydrotreater. The primary product is the methaformate, a gasoline blend stock that we normally target for 90 to 92 RON. The benzene is usually less than 1%, and 90% of the sulfur is removed. The light ends are LPG and a hydrogen-rich gas, as well as the H2S from the sulfur that's removed. So both of these streams will need to be sweetened. It's fortunate we are based on a zeolite catalyst with rare earth elements, so the catalyst is not particularly expensive. And the capital and operating costs are pretty much close to a naphtha hydrotreater. For that matter, that's an easy way to capture just what methaforming is. The process flow is like a hydrotreater, except the ethanol replaces the hydrogen, and you don't need a recycle compressor. And the yields are like a semi-regen reformer and isom combined, except that most of the benzene gets alkylated onto toluene. And of course, half of the ethanol, and when methanol is the feed, half of that becomes water. There's no water in the finished product. Catalyst is regenerated about once per month, and the catalyst life is about 5 years. So to see simply why the cost is 1/3 of the alternative, let's look at the alternative that you're all familiar with. Methaforming replaces the severe naphtha hydrotreating. The heavy naphtha is effectively upgraded octane like reforming. Methaforming doesn't need some steps for benzene reduction. It's already reduced. And the methaformer treats the light virgin naphtha much like isomerization. And this is where the 1/3 capital and operating costs comes from. Now, to understand the full value of that, I convert that into the net present value comparison of methaforming to the alternative of semi-regen reforming and its hydrotreater. I focus first on the first column under methaforming, so you understand what the column means. Yields from the methaformer for this 215 KTPA relatively small unit are worth $29 million a year. This is based on US Gulf Coast long-range prices. You'll always want to put your own set of prices in, which we can facilitate. I show here then also CO2 emissions reduction credits of $5 million a year, which for this case is based on $50 per ton for CO2 emission savings. OPEX is 8, much like a hydrotreater. CapEx is 25 million. And for our CapEx, we include a 40% allowance for the off-site battery limits facilities. And so for this relatively small methaformer, we see an NPV of 150. The key is comparing that to the competitive alternative, which is the hydrotreater and the semi-regen, which only has an NPV of 20, giving the Methaformer, as you see in the far right column, a $130 million NPV advantage over the traditional alternative. I see my footnote reminding me that the yields include the combination of fuel gas consumed and produced. It includes the economics for the hydrogen that's produced, which would be pulled from the unit. And it includes the specific RON value, usually 90 to 92. For American customers who are wanting to make a base stock for premium, we've run economically up to 95 RON. This is all good, but there are probably not many new reformers or methaformers to be built in the coming years. And so our largest market comes from converting existing semi-regen reformers, particularly where people don't have already ISOM. And so in the same format, I show converting a semi-regen reformer, in this case, a typical size 860K TPA, or 20,000 barrel per day, with ethanol as the co-feed. And for this case, I would just highlight, let's look at the methaforming advantage to the existing alternative, which would be a hydrotreater and the semi-regen reformer. You'll see that the yield credits are over $30 million a year. Most of these yield credits come from the fact that the methaformer processes the light virgin naphtha, which is not being upgraded in the alternative. The CO2 credits become much greater because this is a much larger unit at $22 million a year. Operating costs are significant, shutting down existing unit. And I show a CapEx estimate of $20 million. This $20 million is to allow for 2 large size, 1 space velocity, redundant reactors. When we're converting a semi-regen reformer, the simplest way of that conversion is actually of the naphtha hydrotreater in front of it. In this case, the 2 new reactors, larger reactors, are installed while the unit is running, making for a very quick conversion. An alternative that saves on reactor costs, but will have more piping changes, would be to use the existing reformer reactors, which have enough capacity for the needed space velocity, and rearrange them in a methaforming mode. That would take a longer downtime. As you see in this case, the NPV advantage of methaforming over the existing semi-regen is 400 million NPV. This is including the CO2 credits, and for places who won't have those yet, the NPV advantage for the conversion is still quite substantial at $250 million. Basically, you can see the $20 million CapEx is paying out at $30 million a year, so much less than a 1-year payback, even without the CO2 emissions reduction credits. This is the main and the most common application, but we have another application that also has CO2 emissions credits, and that's for treating of the light virgin naphtha, or any naphtha for that matter, where the refinery has FCC dry gas. So in this case, it is the LVN, and the co-feed we're using is ethylene. The methaformer has the capability of reactively extracting the ethylene and the little bit of propylene that's in the FCC dry gas to serve as the co-feed. This provides particularly good economics in that the ethylene is currently realizing fuel gas value, And by putting it in the methaformer, it's recovered to get gasoline value. So in this case, I'm comparing a new 190K TPA methaformer with an alternative of isomerization with recycle, one that's more expensive than simple isom, but gets much higher octane. And I once again focus on the column at the right, which highlights the difference. And so the basic yields of the methaformer are comparable to that of the isom with recycle. And in this case, you'll see we get 5 million a year of CO2 emissions reduction credits. OPEX is a little less for the methaformer. Methaformer, remember, doesn't need hydrotreating in front. And the CapEx is significantly lower for the methaformer, giving a NPV of $85 million. And this is all using the typical worldwide value of CO2 emission credits. Currently in California, the value of these credits is $200 per ton, 4 times the numbers here. So that becomes, and I think I can go back here, for this conversion of semi-regen, this 22 million that you'll see for the CO2 emission credits becomes 4 times that, 88, which really dwarfs the economics. And this is why we're doing a significant marketing effort, talking currently with a couple of refiners in California for taking advantage of this special environmental opportunity. To review quickly where methaforming came from, the catalyst and process has been designed and optimized with over 7,000 hours of pilot plant testing. The bulk of the testing has been with the 100 milliliter lab facility that we use for testing different types of naphtha. Specifically, we've tested over 50 types of naphtha in over 300 total pilot plant tests. Then our latest and largest pilot plant, which started up in late 2018, is a 9-liter 3-stage reactor. We have, with that plant operations, have confirmed the yields that we've seen from the smaller pilot plant. We've also observed that the benzene reduction is better, consistently below 1% with the 3 stages. This is because the benzene that's produced in the first 2 stages gets another shot at being alkylated by the alcohol addition to the 3rd stage. Additionally, the 3-stage plant gives us design parameters for our first major commercial unit. A commercial unit would be built in a 3-stage operation in which 1/3 of the co-feed, ethanol or methanol, would come in with the feed, and then at the beginning of the 2nd and 3rd stage, the remaining 1/3 and 1/3 of the alcohol is injected. We have much interest in this process for locations that have stranded naphtha. And for that, we have worked with a Russian EPC company to develop the detailed mechanical design for some modular skid-mounted methaformers ready to order. We have 2 sizes. One is the 6K TPA unit at a cost of $900,000 FOB Black Sea, 6-month delivery. The more popular one is the 21K TPA unit at a cost of $2 million FOB Black Sea with a 15-month delivery. Now, the skid-mounted unit includes all the inside battery limit facilities needed for it, and the outside battery limit would need to be designed and provided by the owner, much of which already exists. The offsites include the feed and product tankage and the alcohol receiving and tankage facilities. for locations that will be blending finished gasoline with alcohol, with ethanol in it. Those ethanol facilities will already be there. As I mentioned earlier, the hydrogen-rich gas and the LPG will need sweetening. And for utilities, we need the normal suite of fuel gas, electricity, wastewater, flare. The process, Methaformer itself produces enough fuel gas for itself. Some of the customers have targeted to use bottled LPG for startup fuel gas, not needing to connect to the fuel gas system. These are quite clever and popular units. We have several other refiners under discussion. Each time I talk about this, there's a little change in them. But at the top of the list every time is our major Russian refiner, Gazpromneft, who has been keen on methaforming and important in its process development. They're targeting a 470K TPA unit to start up in 2023. They funded 50 feed-specific pilot plant tests that were using raffinate, a benzene precursor naphtha, as well as light FCC naphtha. And in their case, they have the advantage of available FCC dry gas to supply low-cost ethylene. These initial tests all look quite attractive to them, and as a result, they funded our new 3-stage 9-liter pilot plant to further confirm the design parameters of this big commercial unit. At the same time, we've been in discussions with several refiners in the Russian area, one of which I mentioned is in Uzbekistan, who's looking at a 21K TPA methaformer, which would likely be one of the modular units that I showed you on an earlier slide. They've already run 3 sets of pilot plant data and are quite, find the yields quite attractive. None of these are currently looking at CO2 emissions credits. I also am in discussions with a couple of merchant refiners in the US. In that application, they're looking to convert 55K TPA of low-cost spot purchased, opportunity priced naphtha into finished gasoline. One of the beauties of the methaformer, it's quite tolerant and effective on a whole range of naphthas, and so whatever they can buy at a good price, we can effectively process it. And for that one, we're looking at, or they are looking at, a local manufacturer to do a skid-mounted unit, modular based. For after they build one, they are looking to do more. And the targeted ex-works cost of that is $3.5 million, following US design criteria. Now, whenever I get refiners around, I always want to make sure they're aware of a special opportunity. Well, not a special deal, but a special opportunity. It's very economic to convert an existing idle hydrotreater or reformer into a methaformer. You saw from before the process flow was so similar. We estimate for less than $5 million, you can convert an existing idle unit. And if you have, and part of that cost is the ethanol receiving and handling facilities. If you're already blending gasoline with ethanol, then costs can be less than $5 million. So these units would pay off in much less than 1 year and would be a very effective way of proving the technology. So normally in the conference, excuse me, I would ask, do any of you have a idle unit in your plant? And you raise your hand, and I'll ask you in the chat. You can raise your hand in the chat and let me know. So let me summarize. With methaforming, you can produce gasoline from naphtha with ethanol, methanol, or FCC dry gas at 1/3 the cost of current technology with comparable yields. In so doing, you would be upgrading the naphtha by $100 to $300 a ton. And our new focus with the growing international focus on CO2 emissions is that our process reduces those emissions by 1/2 ton per ton of naphtha when your co-feed is ethanol or ethylene, would be from FCC dry gas. So if hearing this, you see an opportunity in your refinery for the inherent economic advantage of methaforming with methanol or ethylene from FCC dry gas, and particularly if you anticipate CO2 emissions credits coming in your area soon, let me know. Let me know what the naphtha that you have is, and we, based on all of our pilot plant tests, we can predict for you the yields you can expect. I show below the contact information for myself and for Dennis, who heads up our technical team in Moscow. I look forward for your questions, and I hope to have entertaining answers. Normally I'd say I also look forward to meeting you during the happy hour, and I do look forward to that. Next time we are together in person and have a happy hour like that. Good day.